Okay, so this is cis256. Today we're going to talk about a new data structure, which is very useful and with very good properties. And data structure is called hash table. So what is a hash table or hash algorithm? So in previous algorithm like list and other data structure like stacks and queues, the general searching takes best like O log of n if the list is sorted. If not, then it's O of n, right? And when you sort a list in general, it's either n log n or n squared running time. But hash table or hash function can achieve O of 1 time, which is constant, which is awesome. So how this hash table is can realize this, right? So and as you know, O1 just means the um, the searching time is not a function of size. So no matter how big is your hash table, it always take almost constant time to find the item you want in this data structure. So imagine if you are Google search or put your search result in a hash table, then it will really be very fast to search whatever you want, right? So this is also possible with the hash searching techniques. Okay, so from the Wikipedia, you can see a definition of hash function. A hash function, just like what's in this picture, is basically a function. A function is basically something to map input to the output, right? In this case, input is, we call it keys. So the keys can, should be unique, right? And each keys can be hashed to a index in array, which is typical implementation of hash table. So the idea is, given the input, I can calculate the keys, and then again, we find the location in the array. Hopefully, it'll be one-to-one mapping, and it's constant time. Depends on how fast you can calculate the key from the input. Okay, so that's the definition of a hash function. Again, some terminology, the values returned by the hash function, we call it hash values or hash codes or simply hashes. Okay, so some more definition, like the function, hash function can simplify by the h of item. The item will be input of the data sets. So typically we map it to an array of size m. So the hash value ideally would be also fall into the range of 0 to m minus 1, right? And then typically that hash value become indexed into array, list, or table of slots. Now, so a typical function that can satisfy all these property is modular function. Remember modular? It gives you a nice property, but at item modular m, the maximum number that it can come out is less than m. Right? 0 to m minus 1. So that satisfies the property number 2. So modular function is pretty popular or typical for a simple hash function. Okay, so here is a detailed example. You have items, which is a number, integer. And if you do modular 11, so you have a table size 11. And if you modular 11, each number will give you a different hash value with 0 to 10. Okay. And so we can organize this number into, so 77 will be hashed into index 0. So the index 0 will be have 77, 26 is 4. And so you fill in these numbers. And those empty slots, we put a none in it to begin with. So they indicate empty slots that you can put in more data. Okay, so that's a basic, example of a hash table. Okay, so now let's define it in Python. So In Python, we just use the list to indicate a hash table. Initially, these 11 slots are all none, okay? And then the hash function is simply take an item, which is integer, return the item modulo 11, okay? And that will get hashed to a value between 0 and 10. And when you put the item in, you can put it to a hash table with index hash or function. And that the content function basically search for that item. You can also put into the hash table and see if that value is equal to that item. Okay, so that's the simple implementation of a simple hash table. All right. So there's some more terminology of a hash table. We define a load factor. Well, load factor is measuring if the hash table is almost full, how full it is, right? There are 6 items that's already filled. So 6 divided by the 11 possible slots is 54.5% full. So the lambda is number of items in the current hash table divided by total size. That's the definition of load factor. Now, you can see that our hash table is very fast. If you insert anything in the hash table, it takes 01, because all you need to do is calculate hash value and using the list array index to find it and put it in. Now, here is a problem you may found. What if two different value were hashed to the same slot, right? For example, 22, module 11 is 0. So 22 has going into the same slot as 77. Well, 0 is already filled with 77. So what do you do, right? This is called collision, a clash. So a collision is a very often occurred when you design a hash table. So what do we do with that? So you can see that there's a collision of 22 and 17. Okay. So there's more terminology here. A perfect hash, as you can see, is a hash function that creates a unique value, hash value for every item. There's no collision happen in perfect hash. So yeah, as long as your input data is more than the total maximum number size, you will guarantee to have a collision, unless you can have a tip big enough to hold, each item in one slot, right? No 2 items have the same hash value. So yeah, this one is hash value. Okay, very good. Now, but as long as the load is low, the number of slots used for data is just a fraction of the size, right? It's close to 0.1. So as long as, so basically, there's no perfect hash, let's say, right? Because if you design a perfect hash, you predict, every number is contained in our list. The list is big enough. The problem is you have a lot of wasted slots, okay? So we want to minimize the number of collision, obviously. Every time collision happens, we will deal with it, but that will increase the total running time, right? It's not 0.1 anymore if you have many collisions. So we also want the hash function easy to compute. If we have a very complex hash function, it also takes computation time. So it's not really a 1 anymore. So anyway, for example, there is a technique called folding, right? For example, you want to hash a phone number in US. So how are you gonna do that, right? Because the area code sometimes, so we can separate in this into some unique pieces like 43. So you can group like every 2 digits into 2-digit groups, and then you add them together in module 11 to get the table size. Okay, that's one way of folding. So you do some pre-processing. The another way is the mixed square method, which you square the number, right? Take like 44 and take the middle of the 2 digits. That's another technique, right? So, so in this case, the advantage is that the adjacent numbers will be hopefully hashed to a fairly different slot, okay? So no cluster happen. So we can take 93 of modulus table size to get 5. Okay, that's another method for hash function. There's a lot of way to do hash function, okay? The idea is to create a less collision. If you have a input as a string of data, you can also, as you know, a string is just a Unicode value, and so you can get an integer value by using the ORD function, right? ORD of C is 9. So these are ASCII numbers in the table. You can use that. So here is a simple hash function for a string. You can convert that to, so you can add all the ASCII number of the character in the string and compute the sum. That's the one of, it's like checksum value of your string. And you can take that string, checksum and the modular number. So that's another way to hash a string. All right. However, this kind of problem is if you have anagram. An anagram is a string that has the same count of characters. If you use a count method or count function, count object on the string, you'll get a frequency table for each character in a string. Okay, how many A's, B's, and C's, so on. And if they're anagram, they will sum to the same number, right? And if you apply a weight to each letter, then you can solve that, right? Because although they're anagram, but if it's in a different position, then they have different weights. So you actually added, so they are different numbers. Okay, basically, you treat this as a number. All right. So how to solve collision, right? So we mentioned collision is the biggest problem in hash table. When you try to put 2 items in the same slot, even if you have you need a systematic way to add them hash table. Otherwise, and not only you have to add them, you also need to have the same systematic way to find it later. Okay, so 2 typical ways called open addressing or unchaining. So open addressing has 3 subcategories: linear probing, rehashing, quadratic probing. And we'll talk about chaining and have a homework on chaining later. Okay, so linear probe is one of the simplest way. You have a list, right? You have a underlying data structure to store hash table. Okay, hash value. We insert item into the hash according to a hash function. If the item is already in the slot is occupied, now you have a collision, right? So what do? You find the next slot to the right of that slot, which is empty. Okay, if it's not occupied, keep going to the left. To the right until you find an empty slot and use that for the new item. Okay. Now, that's you install it. When you want to find the value with the hash table, first of all, you hash it, right? You go to the slot and you find, oh, there's something already there and it's not what I want. Now, are you giving up? No. If it's not slot, then continue check each slot to the right. If a slot is empty, then return false. Otherwise, if slot has item, return true. So basically, if you have a collision, you have to search every single adjacent slot until you find that item. Think about it. Right? According to your algorithm, when you insert it, you go to every single slot, first non-empty slot. First empty slot, you put it in. So if you also encounter the empty slot and you don't find it, then that means you have no such added in the hash table, right? But also it means the linear search. So to search is O of n, right? The worst case scenario, you search all the tables around and you find that item. Or you didn't find that. Either way, it's O n. So if a collision happens in this linear probe, it's O of n. here example 44 is hashed to 0 modulo 11, and I have to put it into slot 1 because 77 is already there. Okay, now 55, because it also hashed to 0, you go to 77, 44, and go to slot number 2. All right, so it's linear in inserting or searching for the open network. For the linear probe. So now we have a cluster of 0 and 2 that all hash the same value. It's affecting it's really effective trying to insert 20 because slot 9 and 10 are also used, right? So now you have to go all the way 20 divided modulo 11, right? So it's like 10. It's already, you have to go all the way to number 3. And then you put 20 in, right? So here is the explanation of that. So 20 modulo 11, slot 9, but it's occupied. So go to 10 occupied, and you go around the table, 0, 1, 2 occupied, and you put it 3. All right. So the problem with linear probing is that the numbers that hash the same value tend to cluster a lot of items in the adjacent slot. It's called clustering. When that occurs, it tends to propagate. Since more adjacent slots are filled, tend to cause more collision, cause even more clustering. So that's the problem. How we solve that? Well, you can use rehashing. So rehashing, instead of just picking the next empty slot, we go to a certain distance to the right called the skip distance. So we skip certain distance and pick one. So basically your rehashing is your position plus some fixed skip value and you rehash again. So this will prevent clustering, right? You no longer go to adjacent slot, you go into some skip value. And when you pick up the skip value, when you pick the size of table, it is better to pick a prime number, right? That give you, best result. So there's a third way, it's called quadratic probing. So basically, like every time you have a collision, right? So instead of doing a fixed skip, you add a constant to the skip every time. So skip values could be, so your skip value is not constant anymore. So every time you have a collision, you add 1, this is first, adjacent, and 3 and 5. So every time you have a collision, you add more skip to it. So this will lead to quadratic probing, okay, to further solve the clustering problem. So next is chaining. So another idea, instead of doing like, linear probing or rehashing or, quadratic probing, when you add the slot where you have collision, you can have a linked list on that slot, right? You no longer go to adjacent slot. You still stick to that slot as the head of the linked list, just like a chain, right? So basically, in the picture, you can see 77, 44, 45, 55 is all hashed to 0. And instead of just doing open, going to the right, you can stay at the 0, but at the 0, you create a list, okay? So whenever you have a 77, you go next to the next, you expand that. And then when you are searching for it, it go to 0. It's not 77, you keep searching for the linked list. So that's called the chaining, right? It's chain the number together. All right, so this is another way to address the collision, and we'll use that in our assignment later. Okay, sounds good. Thank you, and have a good day. Bye.